Welcome to the Explainer. Today, we're taking a look under the hood of the Merg-E programming language to break down exactly how it implements rational and complex numbers. We're going to keep it strictly to the architectural nuts and bolts, why these specific numeric types are necessary, and how they actually function mechanically. Let's get right into it.
So first up, why add the division sign, the obelisk, and the inverted exclamation mark to a programming language in the first place? Well, as Merg-E prepares for its version 0.4 specification, these operators are practically being pulled in. And when a language introduces new operators like this, it's pretty much always driven by structural necessity, not just, a cosmetic coat of paint.
It really comes down to the fact that cryptography is treated as a first-class citizen here. Merge is built specifically as a domain-specific language for Web3 applications and Layer 2 nodes. Because it leans so heavily on cryptographic algorithms, the runtime inherently demands a mathematical baseline that's just a lot broader than your standard integers and floats. It's about giving developers the tools they need to avoid precision loss when handling really sensitive operations, things like zero-knowledge proofs or elliptic curve calculations.
Now, you might be thinking, doesn't Merg-E already have massive base types? And it does. It has signed and unsigned integers, scaling all the way up to int 16,384 and floats up to float 256. But even with all that raw bit width, the mechanics still require a third and fourth base type, rational and complex numbers. You see, floating point math inherently has precision limits, no matter how gigantic you make it. For certain crypto algorithms, you literally need the exact fractional representation of a rational number, or the multidimensional mapping of a complex number. Basically, raw size just doesn't replace the need for structural variety. Moving on to our next section, adding rational numbers, and specifically, the division operator. The source material actually puts this really plainly. Quote, "This is not a Merg-E language quirk. Many number-friendly languages already have a rational type. So adding a rational type is a completely standard, modest architectural choice. It's not some wild gimmick. It's just a required tool developers expect when writing code in cryptography-adjacent domains, making absolutely sure that fractional values don't lose fidelity through floating point approximations. Next up, let's look at complex number mechanics and the inverted exclamation mark operator. Okay, so why use the inverted exclamation mark at all? Well, in standard math, you'd usually write a complex number with a plus sign, like a plus bi, or even just 12i. But in a strict programming parser, the plus sign is already spoken for. It's an established operator. Plus, 12i simply isn't a valid literal. So to solve this cleanly without breaking existing parser rules or messing up operator precedence, the language uses the inverted exclamation mark. Basically, this mark functions as a literal operator. It's used to formally compose complex number literals out of more fundamental numbers. Think of it kind of like structural glue. It tells the parser exactly how to group the incoming numeric data to form a complex value. This completely bypasses the ambiguity that standard math notation would otherwise cause in the lexer. And mechanics-wise, a complex 32 isn't some brand new isolated data structure. It's actually just composed of a real float 16 and an imaginary float 16, paired together. It's that simple. And this logic scales proportionately all the way up the stack to complex 512, which just pairs two float 256s. It's honestly a very straightforward, practical way to handle complex types by reusing the language's existing fundamental building blocks rather than bogging down the compiler with completely new low-level memory alignments.
So, to bring it all together, the core structural preparations for the version 0.4 specification really revolve around these new types. You've got the division and inverted exclamation mark operators being pulled in for specific parsing roles. Then you have the third and fourth base number types stepping in to handle exact fractions and complex math. On top of that, the plan is to expand the existing integer length generics into rational length generics, which will just give developers a lot more granular control.
Which brings us to a final thought to leave you with today. How will rational length generics ultimately shape the underlying mechanics of cryptographic domain-specific languages? As languages like Merg-E evolve their foundational numeric types, it opens up some really interesting possibilities for how we efficiently structure cryptographic data right at the compiler level. Definitely something to chew on as you explore systems architecture. Thanks for tuning in to this explainer, and I'll catch you next time.